Yeah, great. So I'll start off by saying that I'm not a computer vision person or a vision science person, so it's been a lot of fun being at this workshop and learning about what all of you work on. I went to CVPR for the first time a couple weeks ago for a couple days, so it's been fun to see more of that. So with that said, also, if I use terms that you don't understand, if you have any questions, please interrupt, ask questions. I'd love to have a discussion about this sort of stuff. So yeah, so let's get started. I want to start by giving a bit of an overview of machine learning, and I think where things are at least right now in the machine learning field, which is there are some big success stories, things like object detection, machine translation, speech recognition, and these systems work really well, and they're really useful. By using deep networks, they can handle raw sensory observations, like image pixels, like speech, audio waves, and they can also handle the diversity of the real world. You can deploy them and have users upload their own images, upload their own speech, and these systems work pretty well on those data. But from the perspective of building artificial intelligence, I think these systems are a bit dissatisfying. Because the way that they learn is through massive, large labeled data sets. They require very detailed supervision in the form of labeled data, and they learn completely passively, which means that they require a human in order to improve, in order to continue to get better. So, well, one natural question is, how can we move away from such strong supervision and build systems that can learn in more autonomous ways? And one way to do that is by having agents that interact with the environment and collect their own data and learn from that interaction. And there has been exciting advances in this area too. Things like we've seen agents that can learn how to play Atari games from raw pixels, become the kind of the champion of Go. And these systems are also really impressive. They can handle raw sensory observations like image pixels, like kind of game states in Go. And because they can interact with the world, they can learn from higher level feedback such as rewards. But one thing you might notice here is that these domains on the right look a lot different from the ones on the left. They're all in simulation domains, closed world domains that lack a lot of diversity. And further, because they're using very expensive reinforcement learning methods, they require very, very large amounts of supervision. So while you can have them learn from fairly high level reward feedback, they still often usually require fairly detailed supervision of that form. So kind of this motivation brings me to my work. In my work, I'm interested in, can we reduce some of these limitations, and can we enable agents to learn generalizable skills in the real world? And by the real world, I mean robots. Robots like this, for example. You might ask, well, why robots? Robots seem like they're a bit of a hassle. Why not just kind of download your data set, work with that? And the reason is I think that robots can teach us about artificial intelligence. I think they can teach us about what it means to be intelligent because, well, of course, these robots aren't very intelligent right now, but they are faced with all the complexities of the real world. They're faced with the ability to generalize across objects, across tasks, across environments. They need some sort of like common sense understanding of the world in order to perform well. And supervision can't really be taken for granted in this situation. You really need to think critically about how you actually help these systems learn in the real world. Okay, so what should we have these robots do? That's kind of one question. And given that there's been a lot of impressive feats in artificial intelligence, it's like it seems very natural to think that we can get these robots to do very complex things as well. So we've seen AI systems that can do incredibly impressive things, like becoming the champion in AlphaGo, like translating between two languages. These systems are really impressive because they can perform a complex task extremely well, sometimes even better than a human. So how close are we to building like superhuman robots that can operate and do things way better than humans in the real world? Well, it turns out that even like basic, simple, yet general manipulation skills are well beyond the scope of our current methods. Even things like manipulating Go pieces are much harder than kind of the things that we can do today. How is this the case? Well, it turns out that and this gets back to actually one of the talks yesterday, is that the simpler, broader capabilities are really, really hard. Because they're so intuitive, no one taught us how to manipulate objects, no one taught us and gave us lessons on how to see. They're so intuitive to us, and it turns out they're actually harder than the more complex things. And this is exactly what Moravec's paradox states. It states that the things that are simple and intuitive for us are harder to create in artificial intelligence systems than the more complex things like playing Go, for example, or playing chess. Okay, so in this lecture, I'd like to talk about how we can build robots that can learn to interact with the world, learn manipulation skills. This is what I'll call Visuomotor learning, in the sense that we're actually going to be learning both perception and control in order to perform tasks in the real world. Okay, great. So to start off, I'd first like to contrast what kind of a typical computer vision task looks like and what learning in the real world looks like. So a typical computer vision task is something like object classification or object detection. This is inherently a supervised learning problem, where you have some large data set and you learn to kind of produce the labels of that data set. Whereas in things like object manipulation, you inherently have a sequential decision-making problem, in that you're going to be making decisions at multiple points in time, and your decisions at one point in time will affect the states and the observations that you see in the future. So while in supervised learning we have IID data, we have data that is independently and identically distributed, and we have a validation set that is from the same distribution. In things like object manipulation, your action that you take, the decision that you make affects the next state that you're in. And also in object classification settings, you assume some large data set that's labeled and oftentimes curated, has particular viewpoints that are determined by humans. Whereas in things like object manipulation, we have to actually collect the data ourselves and figure out how we want to collect that data. And we also need to figure out what are the labels, what should we be predicting, what should the supervision even look like? And lastly, in things like object classification, we have a very well-defined notion of success, which is like accuracy on the test set, for example. Where in things like object manipulation and interaction with the world, we actually need to kind of come up with our own success metric as well. So all these challenges make things substantially harder when we actually want to interact with the real world. And in this talk, I'll talk about how we can overcome some of those challenges and how we can develop techniques for actually interacting in the world. Okay, great. So an outline of what I'll talk about. First, I'll give some background on reinforcement learning. Then I'll talk about model-based reinforcement learning methods, which have a lot of benefits over other reinforcement learning methods in terms of their applicability to real-world problems. Then I'll talk about model-based RL with image observations in particular, which introduce a number of additional challenges. And then finally, I'll talk about some open problems in kind of this realm and some initial approaches for trying to tackle them. Okay, and it's worth mentioning that this will be a mix of a kind of a tutorial style thing where I'll be kind of introducing some of the methods and approaches for this, as well as some research and things that are a little bit more kind of cutting edge and in terms of the techniques that we've been developing. Okay, great. So let's get started on some background in reinforcement learning. So first, I'll start with some terminology and some notation. So in kind of a classical computer vision problem, you might be trying to take in an image like this and produce some output. For example, classifying the kind of animal this is. And in this case, we'll be using O to denote the inputs and A to denote the outputs. And those are going to stand for observation and action. Now, one of the first differences that I mentioned is that instead of making a single prediction, we're going to be making predictions sequentially. So each of these will have a time step, t, corresponding to the time in which you're making that decision. And of course, your action at one time step will affect the observation that you see at the next time step. Okay. Now, of course, we aren't going to be doing things like classification. These actions will actually correspond to things that we might do in the world. So things like running away, like ignoring the animal or petting the animal. And so these actions will correspond to like actually physical actions that we'll be taking in the world. Although, of course, the formalism of reinforcement learning goes beyond actual like things like robotics, where we're actually physically taking actions. Okay, so O is going to be the observation, A is going to be the action, and this object pi, which is going to be a neural network in many cases, is what's called a policy that's mapping from observations to actions at each time step. Okay, and it's also worth mentioning that there's also this object called a state, S, and in a fully observed setting where you can directly observe all of the relevant variables in the world, then you are learning a policy that's conditioned on states rather than observations. And so to kind of see this difference, if this is if you're an animal trying to chase some prey, this might be an observation that looks like this, an image of what you see, whereas something like a state might correspond to the poses of the positions and orientations of the animals in the scene. This is kind of the most concise representation of the world. Further, if you're in a partially observed setting, you may not be able to actually see some of these things, like maybe there's occlusions or something, and that's kind of what's referred to as partial observability, where you can't actually observe everything directly. Okay, great. So it's first worth mentioning kind of a very simple approach for trying to tackle this problem, trying to learn a policy that produces actions, and that's known as imitation learning. And imitation learning basically tries to reduce the problem of learning this policy to a supervised learning problem. And so say, for example, you're trying to learn how to drive a car. Your observation is the image that a camera takes from your dashboard, and your action is whether or not to turn right or to turn left. In this case, what you could do to try to solve this problem is you could actually collect data of human drivers, record the observation that they see from the camera, record the actions that they took, which is the steering angle, put this into a large training data set, and run supervised learning on this policy. This is something that's quite simple and has been applied towards some real-world problems. There are a number of challenges with it, such as basically issues of compounding errors. When you're taking actions and you make a mistake, you'll end up in a state that's dissimilar from what you've seen before, and you'll eventually go off the path of the data that you're seeing and make more and more egregious errors over time. So this is one approach for learning policies from images. What I'd like to focus on today is more of reinforcement learning approaches where we're learning through trial and error rather than through large labeled data sets. Okay. And then the last object I'd like to introduce, which is what's known as a reward function. And this is determining whether or not a good outcome is good or not, which actions are better or worse. So a reward function typically operates on a state and an action, and it tells us which states and which actions are better. So it typically outputs a scalar value that tells us how good a state and action are. And so if you're driving on a highway in a nice car, that might be something that's high reward. And if you get in an accident, that's something that would be considered as lower reward. Okay. And then the state, action, reward, and this transition function are dynamics, the next state given the current state in action, define what's known as a Markov decision process. Okay. So now that we've defined notation, what is kind of the goal of reinforcement learning? So we have our policy. Our policy, in this case, will be a neural network. It has parameters theta. It takes in a state, outputs an action. This action is given to the world, and the world gives us a new state, S prime. And then we take this S prime, give it back to the policy to determine our action at the next time step. This can be viewed as this kind of graphical model right here, where we have states and actions that affect the next state, and the observation is a function of the state. And then our goal will be to learn a policy that maps from observations to actions. And this edge right here is representing, or these two edges are representing the dynamics of the world of what the next state will be given the current state in action. One brief property worth mentioning here is that these dynamics are independent of the previous states. This is what's known as the Markov property. It essentially says that the future and the past are independent given the current state. Okay, and then kind of the goal of reinforcement learning is to learn a policy that maximizes reward. So it looks like something like this, where our goal is to maximize the expected return. This is an expectation because the dynamics may be stochastic, our policy may be stochastic, and the expectation is over the distribution over states and actions that we'll see by executing our policy. This is what it looks like in the infinite horizon case. And in the finite horizon case, where we only have t time steps to operate in the world, it looks something like this. Question?
Is there a useful difference to be made between, like, the state inferred by the agent and the true state of the real world? Because what it looks like is once you take an action, the state dynamics occur on the true state of the world, but the agent doesn't know the true state. They only get the observation. So is there like a useful difference to be made there?
Right, so the dynamics operate on the true state of the world. In many cases, it's sufficient to make a modeling assumption that the true state is what you're observing, and that you're actually dealing more with states than with observations. Does that answer your question?
No, I'm just more curious as to how does this link with traditional partially observable environments where you have a belief state and separate from a true world state, and here are they both constrained to be the same?
Right, so if you can't observe the state, one approach for doing that is to try to have some belief over the state that you're learning. There are different assumptions with regard to your ability to kind of represent this state space. Like maybe you don't even have any representation of it and you need to learn a representation of what that state is. But one viable approach for solving the partially observed setting is to form some belief and just run regular reinforcement learning on that belief state and treat it basically as the fully observed state. Okay, any other questions? Okay, so this is the general problem setup. Now let's go over kind of just very briefly what different reinforcement learning algorithms look like. So typically they have three different steps. One is to generate samples. By samples, I mean generating trajectories in the environment, by essentially running the policy in the environment. Then once you have those samples, you typically fit something to estimate what the return is, given your policy. And then once you have that estimate of the return, you try to use that to improve the policy by trying to maximize the return with respect to your policy. So different algorithms essentially correspond to doing different things in these green and blue boxes. So something like a policy gradient algorithm will try to estimate the return using what's called Monte Carlo by summing up the discounted returns, where gamma is the discount factor. Something like actor-critic methods or Q-learning methods try to fit a Q function to your data by using dynamic programming, by bootstrapping off of Q values at future time steps. And things like model-based algorithms try to actually fit a model to your dynamics of the kind of the next state given the current state in action and use that to improve the policy. The different ways to improve your policy using these estimates. For policy gradients, it's simply kind of deriving the gradient with respect to the reward. For something like Q-learning, it corresponds to taking the max of your Q function with respect to your actions. And for something like model-based, the goal is to optimize your policy with respect to your model by, for example, differentiating through your model. So this is kind of a very high-level overview of different reinforcement learning algorithms. You could teach an entire course on this, which I don't have time for today, of course. And in this lecture, I'd really like to focus on model-based methods and how they can be applied to visuomotor control. But if you have any questions on the other kinds of reinforcement learning algorithms, I'd be happy to take those offline as well. Okay, great. So let's get into model-based reinforcement learning. First, I'd like to give kind of a brief primer of what these kinds of algorithms look like. And the main idea here is just to learn a model of the environment of the next state given the current state in action. And one of the reasons for trying to use these kinds of algorithms is that first, it often leads to better efficiency because you can fit this model with supervised learning on large amounts of data without any supervision. And the model can often be reused for different tasks because it's agnostic to the reward function that you're training on or the task that you're trying to do. So what this looks like is we first estimate a model of our dynamics. We're going to use F phi to denote what the parameterized model, which will be something like a neural network. And we can train this with supervised learning by simply minimizing the difference between the policy's outputs and the actual observed next states. And then once we have this model, what we can do is we optimize this model, which I'll talk about next. Okay, so once we have a model of the environment, the first approach that we can do is just to backpropagate through the model into the policy. So say we have this computation graph right here. We have a policy that's outputting actions and a model that's predicting the next state given the current state and current action. We additionally assume that we have some model of the reward function, the R of S comma A. This can be fit, or maybe in some cases you actually know what the form of that reward function looks like. And so what you can do is you can backpropagate the sum of rewards into your policy parameters theta. So what this looks like as an algorithm is first you can run your base policy. It could be like a random policy, for example, to collect some data, then learn a model fitted to that data, backpropagate through your model, through your learned model into your policy to optimize it. And then run your policy, pi theta, to collect more data, use this to refit your model, and iterate. Okay. Does this all, yeah?
So I got a question. How do you know ahead of time how big your policy has to be, like the scope of, because it could be extremely deep hierarchically. Is that a design decision that gets established before running the algorithm? Or, okay.
Yeah, so typically it's just like, a design choice, a hyperparameter.
I see.
Yeah.
Okay. Yeah. So it's not something that's usually estimated during the process as well.
Correct, yeah. Yeah.
Does the state of the world include the internal state of the actor or the robot in this case? So like it has a representation of its current position?
Yeah. So in something like object manipulation, for example, it could correspond to the positions of all the objects in the scene and the robot's like joint angles, the position of its end effector, things like that. Yeah.
With the model-based, we always based on the policy-based method, or it can also be value-based.
So this is kind of a pure model-based approach. You can also combine like model-free, like value-based approaches with model-based, where instead of backpropagating the summed returns, you can at some point estimate the value of a state and backpropagate the value into the value plus all the intermediate rewards into the policy. Okay. Cool. So this is like kind of V0. Now, how can this approach fail? One of the challenges with this approach is that this policy optimization is going to exploit imprecisions in the model. If your model is inaccurate in some places, it's going to find the places where your model is inaccurate and take actions that get to those states. For example, if your model thinks that you might like if you take a certain action and you're going forward on the road, it actually thinks that thinks that if you go left, you'll actually go forward. Then the policy will exploit these. And one of the things that you can do to help this is by actually refitting the model with on-policy data. That was kind of the step 4 that I mentioned in the previous algorithm. But generally, one of the challenges is that learning a single good global model across all of your states is really hard. Because you need to cover all the states that your policy might try to visit in the optimization step. Okay, so one of the things you can try to do to mitigate this is to actually plan using your model and actually replan at each time step to try to correct for model errors. And this is what is known as model predictive control, or MPC. What this looks like is we first run our base policy, learn a model, backpropagate through the model to choose actions. In this case, we don't actually have an explicit policy object. We'll just be optimizing for actions, a sequence of actions, a sequence of open loop actions. Then we'll execute the first planned action in the world, observe the resulting state, add this state to our data set, and then choose actions again. So we'll take an action, observe a next state, and then replan according to our model. What this can allow us to do is if that first action, if we made a mistake because we were exploiting our model or our model was inaccurate, then we can observe another state and correct ourselves by replanning. So this can help in settings where we can kind of continue to basically try to correct for our model online. And this approach actually works surprisingly well for mitigating model errors. Yeah.
So the idea is you make the step, and then you go back to where you were and replan and do it again.
So you take an action, you observe the state that you're in, and you say, okay, now that I'm in this state, what action should I take? And that state may not have been what I was expecting before.
Right.
And so if it wasn't what you're expecting, then when you replan, you'll kind of instead correct for the error that was made in that first action. Does that make sense?
Yep.
Why skip step 2?
Sorry, what?
Why do you skip step 2 on the way back? Will you go 5 to 3 rather than 5 to 2?
So there's an additional arrow here. So you're correct is that we should actually continue to update our model using this data. In practice, you don't want to be it's hard to simultaneously be training your model and in real time replan. So typically within a trajectory, you will be kind of continuously replanning. And then after a batch of trajectories, you might use that to update your model using the new data collected. Okay, great. So kind of the takeaway here is that replanning can really help with model errors. It doesn't help in all cases, and one of the downsides with this approach is that it is quite compute intensive, because at every single time step, you're going to be planning which actions you should take.
Is an implicit assumption of
Yes, absolutely.
And this is empirically okay, or it's proven to be okay.
There are certainly people who have looked at this theoretically. It's empirically okay in some situations, not in all situations. And theoretically, you'd have to characterize what the errors look like of your model. And that introduces a number of assumptions. Yeah?
If I understand right, you planned a sequence of actions, you took the first one, and you go back.
Yes.
So why did you plan a whole sequence? Why didn't you just plan one, take it, and evaluate? What's the purpose of those additional events in the sequence?
Yeah, so this depends on what sorts of, I guess if you have a model of what the value of the next state is, then you could just plan one step into the future, because you could say, if I take this step, I'll end up in this state, and what is the value of being in this state? If you don't have that value function, if you can't estimate how good it is to be in that next state, then you want to roll out further and say, okay, if I take this sequence of actions, what are the rewards that I'm accumulating over that sequence? So it depends on whether or not you think you have a good value function or not. If you have a very good value function, you can just plan one time step into the future and do exactly what you said. If you don't, then you want to come up with a plan much further into the future and look at the rewards that you're achieving in the sequence of states that you're reaching.
So it's just a better way to know the value of that next state.
Yeah.
Yeah,
and this is kind of an inherent trade-off between the accuracy of your model versus the accuracy of your value function.
Is this actually a remedy for the problem you mentioned before, or couldn't in this case also the model exploit these inaccuracies?
So it still will exploit the inaccuracies. This can help. It is one remedy. In many situations, it actually works surprisingly well. But there are situations, like if your model isn't accurate enough in parts of the state space where it needs to be, then the exploitation will still happen.
Yeah, I'm just wondering why model predictive control should lead to a more accurate model by default.
It doesn't necessarily lead to a more accurate model. It allows you to correct for inaccuracies in the model in real time, potentially. Okay, but it's certainly still not it can help, but it doesn't work in all cases. Okay, and then I want to talk about one more approach for mitigating model errors that can also help in different settings. And the key idea is, instead of trying to learn a single global model of all that works across all of your state space, it's instead to try to learn multiple local models, local to a set of trajectories, and optimize your policy locally where that model might be accurate, where you think that model is accurate. And so what this looks like is you first run your policy from some initial state to collect a batch of trajectories. You learn a local model around those trajectories. For example, in this case, we'll be using something actually like linear regression, a much simpler model since we don't need to be modeling everything. And then we can update our policy locally using that local model. So if we have a model roughly around those trajectories, we can say that we want to update our policy and constrain it, in this case with KL divergence, to stay close to the policy that we've seen previously, to stay closer to those trajectories. And then once you've updated your policy locally, you can then run your policy, append the visited tuples to your data set, refit your local model, and iterate.
So local with respect to what?
Local with respect to trajectories. Local in state space. Right, and so this is inherently a local optimization. It's not going to be a global optimization, but in practice it can be quite helpful for learning how to perform skills in some local space. And what you could do to learn a more global policy is to learn multiple local policies from different initial states, and then supervise a single global policy to match what all those local policies are trying to do. Yeah.
So when you have a continuous state, is it possible to learn it for every? It's not possible to learn local policy for every state, right? So what do you do there? Or do you learn? Can you learn even for a brand new state a local policy?
So what this local around a set of states, around like a trajectory, for example. And if your policy is kind of executing a sequence of trajectories that stay relatively close to each other, you can fit a model around those and use that to improve your policy. Does that answer your question?
Do you then like interpolate, or do you take the nearest neighbor?
You're still learning a parametric model F. So that can work for states that are nearby the states that it was fit to. Yeah.
What is the KL constraint on? Is it the policy of nearby states?
Yeah, so that's a good question. The KL constraint is on the trajectory distribution, and you can essentially get a bound on the trajectory distribution by constraining the policy. Okay. So one kind of quick case study of how this approach could work well is our objective will be to kind of maximize the reward under the policy. At test time, we want to be able to learn a policy that operates from camera images, from observations O, to perform this task. In this case, the task will be to insert the red block into the shape sorting cube. And what we can do is during training time, we can assume that we know the state of the world. We assume that we can know the target pose of the block, as well as the kind of the current position of the block and the position of the arm. And what you can do is if you know the target position of the block and of the arm, you can take samples for each target position, fit a local model and solve for a local policy for each target position of the block. So maybe one target position is like this, another target position is when the robot is holding the block in a different place. And then use supervision from the local policies in order to train a global neural network policy from raw images. So once you kind of fit these local policies for different initial states and goal states, you can use that supervised learning to train a neural network to learn a policy from raw image pixels. Yeah?
And I think of that local policy thing as like doing like a piecewise linear regression.
Yeah.
In that case, doesn't that mean that until I explore everything, I just don't know what's going on in big chunks of the space? I have no way of
Yes.
generalizing.
Yes, that's correct. It's certainly it's a local optimization, and it will find something from your initial policy that gets close to the goal. But if your initialization is far from that, it won't be able to find the solution.
Is this always assumed that the reward function is already known? It's not need to be learned.
Yeah, that's a good question. Yes, the short answer is yes. At the end, I'll talk a bit about how we can try to mitigate some of those challenges with reward functions. So in this case, the reward function corresponds to the negative distance between the position of the block and the goal position of the block. Yeah?
Are you going to say something about, are there certain problems for which some of these approaches are more appropriate, or I would guess you're not going to tell us that you should always do X.
Yes. So I guess I'll get to that, and I'll definitely discuss that. Yeah.
You have a max theta, so is this like the best estimate of your parameters currently for the policy, or do you sort of marginalize over that as well, your uncertainty over your parameters of your policy?
In this case, we are. Sorry, what are you asking?
So you have a max theta in front of the reward
Yeah.
function, right? Is that like an argument? Are you choosing like the best parameters of the policy?
Yes. Yeah. Okay. So let's look at kind of what this actually looks like. So here's a video of what the learning looks like. You can see the robot is moving the cube to different places. So these different places correspond to different goal positions. And what it's doing is it's learning local policies for each of these goal positions, and then using these local policies to supervise a global policy from images. And so at the beginning, I was starting roughly from scratch, random trajectories executed on the robot, and over time I was able to figure out how to learn a policy that can perform the task for each of these different positions. One other thing worth noting is that during the training, the robot is holding the shape sorting cube, and this is because we assume that we know where the objects are in the image, and so we can determine where the object is if we're holding it because we know where our arm is. And this method won't work in settings where you don't know where the objects are in the image, where you only have image pixels, you don't have a low representation of the state during training. Okay, so this is what the final thing looks like. So in this case, I'm holding the block, and the robot can figure out how to insert the block into the shape sorting cube. It can do other things like screw caps on the bottles, place the claw of a toy hammer underneath a nail. In this case, we're learning a separate policy for each of these tasks using the method that I described. And for each of these tasks, it required roughly on the order of 25 minutes of robot time in order to learn it. And what's, I guess, in my mind, particularly impressive about this is actually learning both the perception and the control for performing the task in this amount of time. Okay. So the benefits of this approach is that you can very efficiently learn complex vision-based skills. The downside is that it requires a state during training. And so if you only have the images during training, you won't be able to apply this method. Yeah?
So you just said it's learning the perception as well as the policy. Do you mean it learns to estimate the distance of the object to the target using pixel values during that 25 minutes time? No.
So yes and no. It is learning all of the vision layers for performing the task. We aren't supervising it based on things like distance. It's supervised based on matching the actions of the local policies. And so there isn't, the intermediate representations that it is learning is for performing the task and not for actually, and not for like some standard supervised learning task, for example.
So you're giving the distance values real time?
It is, the local policies are optimizing for the actions to take from different states, and the policy is optimized to match those actions. Okay. So now I want to talk a bit about how we can do model-based RL when we have image observations during training and we don't have the state during training. And so in this case, I'm going to kind of bring back this graphical model. In this case, you can't observe your states or your actions, and you can only observe the observations during training. And so as a motivating example for this, say you want to use a spatula to pick up the object and put it into a bowl. In this case, you know where the spatula is because you're holding it, but you don't know where the other objects in the scene are. You need to be able to learn just from the pixels that you're seeing in the image. And further, one of the things, getting back to kind of one of the questions earlier, is that when you have these observations, you also don't have a model of the reward function. You just have kind of the image that you're seeing. So things get a lot harder in the setting. One option for specifying the goal and trying to get a reward function is providing an image of a goal. So in this case, we'll be providing an image that looks like this, as well as the goal position of the robot arm. And then there's a couple different approaches for trying to solve this problem. So one is to try to learn a model in latent space. So learn some latent representation and fit a model in that latent space. I'll be talking about that first. The second approach that you can take is to try to learn a model of your raw observations, essentially a model on video. The third approach that you can take is to learn inverse models, which I'll try to cover if there's enough time. And lastly, you can try to predict alternative quantities rather than images or rather than latent representations. Okay. So first let's talk about the models in latent space. So the key idea of this method is to learn an embedding of your observation. This embedding I'll denote as the function g, and then learn a predictive model inside that embedding space. So if you have your graphical model, this can be viewed as trying to learn this function g that maps back into your state space S and learns a model on top of your state space S. There's a couple different approaches, a couple different methods that have used this type of approach. So one of the earlier ones is this paper shown on the left, and we also looked at this approach in a paper from 2016. And so let's go over kind of what the base algorithm looks like, and then I'll talk about the differences between these two papers. So first, we run our base policy. This is the same as before. Then we learn this latent representation of our observations in a dynamics model in that latent representation. Then we use our model to optimize our policy, and then again run our policy, append the visited states and observations to our data set, and refit. Okay. So there's a couple questions here of actually how to actually implement this. The first is, what is our reward function for optimizing the policy? In this case, we'll define the reward function as the distance in the latent embedding space. So we'll embed our current observation and our goal observation and use distance in that embedding space, or negative distance in that embedding space. That should be a negative sign as your reward function. You may also have a reward function that operates on actions that encourages you to use less energy, for example. Okay, so that's what the reward function will look like. The second question is, how do you actually optimize this latent embedding space? There's the two papers that I mentioned do take two different approaches for doing this. So what this paper does is they try to learn at embedding and a model jointly. So what this looks like is actually, it looks like an autoencoder, actually a variational autoencoder that operates over pairs of states, the current state and the next state, and learns both that embedding space and the model in that embedding space jointly with respect to the variational lower bound. Okay. Any questions on this approach before I show some results? Okay. So here's, so before that was showing the goal image that was reaching out the arm, and what you can see here is that this is actually the learned policy for trying to reach that goal image. And you can see on the left the state that it reaches, and on the right you can see some of the predictions from the model when you're actually reconstructing the next state back into the image space. Here there was another example of a goal image, and again the approach is able to kind of figure out how to reach that goal state by running planning inside the latent space.
Sorry, what's the difference between the two images?
One of them is the reconstruction from the current state, and one of them is the reconstruction from the next state.
I see.
I have a question.
Yeah.
How is it different from just directly optimizing without using the latent space? Is there any, what's the advantage?
What is the advantage of using the latent space?
Yeah.
So intuitively, one advantage is that it's more compact, and optimizing in that latent space is more efficient. Because you can apply like different trajectory optimization methods in that more compact latent space. I'll talk about how we get about approaches that learn models on raw images in like 10 minutes or so. But yeah, in general, that's a good point because this latent space is learned simply by reconstruction. One other thing that the latent space gives us is a reward function. So distances in that latent space will be used for determining whether or not we actually reach the goal image or not. So in this case, we were able to learn from raw pixels, and it took about 300 trials for these approaches, which corresponds to roughly around 25 minutes of real time. Okay, and then second I want to talk about this paper here. So in this case, instead of learning and embedding with a variational autoencoder, we're still going to be using an autoencoder, but we're going to be trying to learn a representation that has more structure and is relatively smooth. And what I mean by structure is that we want the latent space to represent different key points in the image that correspond to different objects. And how we do that is we actually impose a constraint on the model architecture. So what we do is we take the features from the last convolutional layer, we take a softmax over the spatial extent of that image to try to kind of figure out what are the places of maximal activation in that image. And then from that softmax map, we can compute the 2D position in that image. We essentially take the expectation of the x-coordinate and the y-coordinate to figure out what coordinate in that image has the maximal activation in that image. So essentially this will correspond to different key points that are being activated in that last convolutional layer. And one of the nice things about this operation is that it's fully differentiable, and it gives us these low-dimensional XY coordinates that would correspond to objects in the image. Basically the things that are needed to reconstruct the image. So in practice, when we train an autoencoder on images, we get things that track objects in the scene. So what this visualization is showing is the different key points over time. So red is the current time step and green is the last time step. And we see that it can essentially extract things like the position of objects in the scene. And so this sort of latent space will be very useful for running model-based RL. Great, so this is, what we do is so this is showing the learning process. At the beginning of the learning process, we actually initialized with a policy that was trying to reach the goal position of the arm. In this case, the goal is to basically push the Lego block to the left. At the beginning of training, it could get its arm there, but wouldn't necessarily be pushing the block with it. And over the course of training, it figures out how to actually push the Lego block successfully to the left. This is a bit of a toy task, of course. So here's what the final policy looks like. It's hard to see, but the black tape is showing where it's supposed to be, where the robot is trying to have it end up. And then we can also give it goals like transferring an object into a bowl. So here's what the robot learned in that case. And then lastly, this is the example that I showed at the beginning, where our goal is to use a spatula to lift up an object into a bowl. And the robot learns a policy that looks like this. And this task is actually quite challenging for a robot because you need to be fairly aggressive with actually maneuvering the spatula underneath the object in order to lift it up. And then you can also visualize the latent space, the features that are learned, because they're representing key points in the image. You can actually overlay them on top of the image. So in this case, the X's are showing the goal position of the key points, basically the embedding of the goal image, and the circles are showing the current position of the objects. Okay. And then all of these were learned in about 11 minutes of robot time, corresponding to around 125 trials. Okay, so now that I've talked about learning in latent space, I want to give you guys a thought exercise, which is, why should we be using autoencoders? Why do we need to reconstruct images? Can we just learn an embedding space and learn a model on that embedding space to predict the next state, and use that next state prediction to learn the embedding? In particular, what do you guys, what might go wrong in this case? Why not just take this approach, or is there something that might go wrong? What do you think?
If you learn wrong embedding and optimize according to that wrong embedding, I mean, you can decide that how will. So rather than shooting an arrow to the target, you can move the target embedding such that,
yeah. So basically what can happen is you can optimize, if you're learning your embedding with a predictive loss, it can learn something such that it can learn a degenerate solution where it's not actually predicting next states. It can, for example, an embedding space of all zeros is trivially predictable, right? And so if you're optimizing with respect to only a model loss, you'll learn a degenerate latent space. Yeah.
Reconstructing the image could also have issues, right? So for instance, if you reconstruct the image, you put equal weight on every pixel. But if you like very small amount of pixels in the image are critical for a decision, those might just be interpolated by the autoencoder, right?
Yeah, so that's this slide. So the benefits of this approach is that we can learn complex visual skills very efficiently. Structured representations enable efficient learning. One of the downsides is that the reconstruction objective might not actually recover the right representation. So for example, in the paper that I mentioned, one of the experiments I wanted to use is I wanted to get a robot to manipulate, to basically throw a ping pong ball, where the ping pong ball looks something like this. This is a low-dimensional grayscale image of the robot's observation. I trained an autoencoder on this data, and the reconstructions that it gave me looked like this. So it learned to erase the ping pong ball. It learned a very, very good ping pong ball eraser, because that was something that took a very small part of the image, and was actually hard to generate and hard to predict. So yeah, this is one of the challenges with these types of approaches. In general, I think that if we build better unsupervised representation learning methods, they might be able to better capture things in the representation. And of course, this paper was actually from 2016, and since then, I think we've actually seen much better representation learning methods, and I think that those methods would be better suited for things like this. Okay, now one aside, it's worth mentioning that these lower dimensional embeddings can also be useful for model-free RL approaches. So for example, you could learn a latent space and then do model-free reinforcement learning in that latent space. People have used this with fitted Q iteration, for example, as well as with trust region policy optimization, and they've learned how to, TRPO is an algorithm that's notoriously sample inefficient, but if you do it in this very low dimensional latent space, you can actually run it on a real robot in that latent space. You can also use the embedding for a reward function. So one paper acquired a reward function using ImageNet features and then ran model-free reinforcement learning with respect to that reward function and got a robot to open a door, as shown here. And then also, if you have a reward function, you can actually predict it to form a better latent representation. And so that has been done in a number of different approaches. One of the downsides to this approach is that this assumes that you have a reward function during training. And in things like video games and in other settings, you absolutely have a reward function. But in robotics, in the real world, it's a lot harder to get that reward function. OK, great. So now that I've talked about latent space models, let's talk about actually modeling directly in image space. And essentially what this corresponds to is action condition video prediction. We want to predict future image frames based on the actions that we take. And one of the first approaches for doing this was this paper by Jin-Yuk Oh in 2015, I believe. And what they did is they trained a neural network. They tried both feed-forward networks and recurrent neural networks to generate frames. And kind of the key components of this is, first, it was actually predicting multiple frames into the future, given the current state, the current image, and the sequence of actions. And they also found that it would be helpful to use a form of curriculum where you first train it for one-step prediction, where you're predicting only the next image. Then you start training it for three-step prediction, where you predict the next three images, and so on and so forth, increasing the kind of horizon of your prediction. OK, so they tried to apply this on Atari games. And one of the things they found is that sometimes it works extremely well. So the left is showing the frames generated by this model, and the right is showing the ground truth frames. And what you see is actually it can make predictions that are up to 100 time steps. And it can make them basically perfectly.
Isn't it because the Atari games are deterministic? Yes,
so that's a good point. This Atari game in particular is extremely deterministic, and it's very easy to predict into the future. In other games, this is less clear. So this is, I think, Sequest. And in this case, it can model the agent very well, but things like where the fish are and the divers are, it fails to model them. And these are things that are actually like critical aspects of the game. And if you mess up on modeling those things, then you won't be able to perform the game. OK, so.
But that's also deterministic, right? So it's basically it's trying to do nearest neighbor, but it doesn't have the capacity to remember the fishes.
In this case, it's not conditioned on enough frames to be able to predict when the fishes will appear.
I see. So the context is not.
Yeah. Yeah. The model itself has like millions of parameters, but so it may or may not be a capacity issue as well. Okay, so what this plot is showing is basically the mean squared error on frame prediction as you predict further and further into the future. And there are some games where this works really well, like Freeway, like the first game that I mentioned, where the error is very low, even as you move 100 frames into the future. And there are other games where things are a lot harder, like Sequest. And there are also settings where the feed-forward model works better and the recurrent model works better. So there's kind of different trade-offs to be had there. So kind of the benefits of this approach is that you can get stability through multi-step prediction. It's potentially useful for control. So they had some experiments in the paper for how you could use this for exploration. The downside is that these synthetic images are a lot easier to generate, and they're a lot more deterministic and more observable than frames that you would see in the real world. And it's also not immediately clear how to actually use these models to plan and to take actions. So what about real images? So next I want to talk about some of the work that we did on trying to use these types of approaches in the real world with robots. And first, let's kind of go back to model predictive control and briefly overview that. So the approach that we're going to take is we're going to run some base policy, such as a random policy to collect data. We'll then learn a model on that data. In this case, our model will be on the raw observation space, doing video prediction. We'll then choose actions according to the model, execute the first planned action, observe the resulting state, and then replan at that state. So this is kind of the outline of the approach that we're going to take. Now, what does this actually look like when you're dealing with images? So what we do is we collect data that looks like this on the left. This data is actually really easy and scalable to collect. The robot is just autonomously, randomly exploring the environment, interacting with objects. We actually ran the robot overnight, collecting data like this. You can also collect data with deformable objects, with things like towels, and this is what the data looks like for that. So this is basically step one, the data collection stage. And then once we collect data, we learn how to predict. So here are some examples of the predictions that we can get. We're predicting what the future will look like based on the actions that the robot takes. And in contrast to model-free approaches, these models capture much more general purpose knowledge about the world because they're predicting what will happen, what the object interactions look like when you take certain actions. And they also use all of the available supervision signal. So they're using all of the pixels in the image to learn these kinds of models rather than just learning from a scalar reward function. And there's also, unlike the latent space representations that I mentioned before and other approaches, it's very easy to apply these methods to things like deformable objects. Because we're just generating pixels, we don't need some representation of objects ahead of time in order to solve the task. Yeah?
Wouldn't this have the same issue that this forward prediction model is not informed by the actual task and could interpolate regions like tiny balls and so on that are, or maybe I misunderstand? Yeah, so it could have those issues as well. One of the benefits, I'll get into these details a little bit more in a couple slides, but one of the benefits of this approach is that if you're predicting the next frame, you have all the appearance information of the objects in the scene from the previous frame. And that can tell you, like, essentially predicting becomes easier because you have the previous frame. Like, you only need to essentially predict the difference from the previous frame rather than learn a compact representation that can reconstruct everything. And so that's actually one of the benefits of these kinds of approaches is that it makes it easier to model those small things because you just need to model how they're going to move in the image rather than trying to have a compact latent space that represents all these objects in the frame. I could imagine if the camera is moving as well, then everything changes, right? And then having this tiny ball also moving might be difficult to differentiate. I mean, unless you know anything about the static scene and the 3D geometry and the camera motion and disentangle all these factors. These videos here are nice in the sense that the camera is static, I would say. Yeah, yes, things certainly get harder when you have static camera or when you have a moving camera. Even with the static camera, we see some of these issues as well. It's hard. Okay. And then once you have this model, we actually use it to plan. And planning is a little bit trickier than what I mentioned before. So one approach for planning is to backpropagate through the model to choose actions. In this case, we're actually going to, instead of backpropagating, we're actually going to be using sampling-based optimization to choose actions. So what we can do is say this is our initial image. We consider potential action sequences, like these two action sequences. We then predict the future for each action sequence, for example, shown here. And then we pick the feature that we like the best and execute the corresponding action. So if we predicted 1,000 different futures, for example, we can pick the future that looked the best, execute the corresponding action, and then we can repeat these first 3 steps to replan and correct for potential model errors. So essentially you can view this as a form of visual MPC or visual model predictive control, where we're actually planning in the raw image space and replanning at each time step. Okay, so this is the general approach: collect data, learn to predict, and then plan using the model. One detail here is actually how do you predict the video? We're going to be learning a model to minimize kind of the next state prediction error. And we use a video prediction model that looks like this. So I don't want to go into all the details here, but some of the key points is that it's a deep recurrent network. We're going to be predicting multiple frames into the future, like the previous paper. It's conditioned on actions. This is pretty critical. And one of the things that we're doing different with this is we're going to be explicitly modeling motion and modeling how pixels will move from one frame to the next frame. And this can be helpful for some of the issues that Andreas brought up. So here are some examples. This is actually, we initially did this work at Google. So here's the robots that we had at Google. Here's examples of the ground truth video. If we took the model that was optimized for Atari frames that generated beautiful Atari frames, we ran those models on this data, and these were the predictions that we got out, which was quite unfortunate. And so we actually ended up having to write a paper on video prediction so that we could actually get models that worked pretty well on this.
And here are some examples of the predictions that we got back in 2016 on this data. And so by explicitly modeling the motion of pixels, it's better able to generate frames and handle the diversity of lots of different objects in the scene. So what do I mean by predicting the motion of objects? So what we're going to be doing is we're actually going to be predicting something that looks like optical flow and applying that flow to the previous image to generate the next image in a differentiable way. And we're not going to require any flow supervision. We're just going to be requiring the supervision of the image pixels. But because we can differentiate through this optical flow prediction and application, we can learn how to do this end to end. So what this looks like is, say we have this initial toy image with a red triangle and a blue circle. We predict basically, in this case, convolution kernels of how different parts of the image will move. We'll also predict masks for which those convolution kernels are going to be applied. And then we apply the convolution kernel, each of the convolution kernels to the image to generate the middle frames, mask out the parts of the image that we want that kernel to apply to generate the next image. So it's essentially predicting how things will move in the form of convolutions, applying those convolutions to different parts of the image in order to generate and can compose the final image. Yeah? So the input image in practice is we use 2 images as input to provide some context. And then we apply and so in this case, the convolutional LSTM is taking in those 2 images as input, and we apply this transformation to the most recent image that was observed or the image that was generated.
So I would say this approach wouldn't be able to have let's say you have a ball, which is one half is white, one half is black. And in the particle sequence, you only see the white side of things. And you know that there is a black side to it, since you are only taking pixels and then trying to rearrange them. You cannot, if you have taken more pixels,
Yeah, absolutely. So there are going to be situations where you're going to see new pixels essentially caused by occlusions. Like if the black side of the ball becomes apparent, then that will be part of the case. What we do to handle that, I didn't mention that detail in this part, but what we do is we actually allow the model to generate both an image from scratch that could include the black part of the ball, as well as an image through this composition, and it's allowed to determine which parts of the image it wants to generate from scratch and which parts of the image it wants to transform from previous pixels.
I see. So basically, we did which part is more complicated, and then so basically part of the image is built in by the location, and part of the image is completely different.
Yeah, exactly. And that allows you, if for example, you're looking at YouTube videos or something. If there's a scene change, then you probably want to generate the entire frame from scratch. Okay, and then one of the things we do is in order to generate multiple frames into the future, we feed back the model's predictions back into the model to be able to transform, to produce more images into the future. And in this work, we trained everything with a mean squared error loss function. Although more modern works are looking at things like GANs or things like VAEs for training these models. Okay, so how this works, actually, the full system. First, we have an image, and we specify a goal. Specifying the goal is actually also quite tricky. In this case, we're going to specify a goal by clicking on a pixel and clicking on where we want that pixel to move in the image. So in this case, the goal is to fold this piece of shorts, and we can indicate that by clicking on pixels. We've also explored other ways to specify goals, and if you're curious about that, I can talk about that as well. Then we run Visual MPC with respect to that goal. So this is the video prediction corresponding to the sequence of actions that it chose through planning. And then we can actually execute that sequence of actions on the robot. And we get actions that look like this. So the robot can figure out that it should pick up the bottom of the shorts and roughly, very approximately fold the piece of shorts. Okay. Now, one of the things I really like to emphasize here is that because we're learning a model, this model can be reused for many different tasks. So it can be used for things like grasping objects. can be used for manipulating shirts, for picking up an apple and putting it onto a plate, for folding shorts, for rearranging objects, for covering an object with a towel, etc. And so one of the things that's really nice is that because we're learning this model that's general towards a wide variety of tasks, we can use that model to accomplish all of these different tasks and a variety of other tasks as well. Okay. And the last thing that's worth mentioning and bringing up again is that this approach was completely self-supervised. There was no reward function that was assumed during training, and really the only human involvement in the process was programming the initial primitives for collecting data and for providing objects during the kind of training process and swapping out objects periodically. Yeah?
Does it generalize to different point of views of the camera or different backgrounds?
Yeah, so in this case we focused on a single viewpoint and a single background, and it could generalize to new objects that it had never seen before, but not necessarily to new viewpoints and to new backgrounds. We have work that is going to come out very soon, where we actually are studying generalization to new viewpoints, to new backgrounds, also to new robots, but that is coming soon.
But without retraining
the key is that you need to train it across different viewpoints, across different backgrounds. I mean, there's kind of the standard machine learning assumption that your training distribution and your test distribution should be the same. And so if you train on a lot of viewpoints, you should be able to expect to generalize to new viewpoints from that distribution.
What do you think about providing objects?
So in the data collection process, the robot is interacting, is taking random actions. We put objects in the bin, have it collect data with that. 6 hours later, we come back, we take those objects away, give it a new set of objects, and repeat. Yeah? Yeah, so one of the things that we've experimented with is learning classifiers that can basically tell you whether or not you've succeeded or not, and that can learn something more abstract. And if you want, I can show you some of that afterwards, but we learn things like learning classifiers of whether or not an object is to the right of another object, irrespective of its global position, and things like that can work well. Okay, so some of the pros of this approach is that we can handle real images. There's very little human involvement, and we can accomplish many different tasks with a single model. And then some of the downsides is that despite the fact that they're real images, there's limited background variability, viewpoint variability. We can't yet handle as complex tasks as the ones I mentioned before, like the Spatula task. And it's also fairly compute intensive at test time because we're actually planning with these large video prediction models in real time. And in practice, we're parallelizing that computation across 4 GPUs. Okay. Now I want to take a kind of quick divergence and talk about some recent research that we were trying to do to handle the second limitation, which is the ability to learn more complex skills. And in particular, what we wanted to look at is if we could incorporate a small amount of additional supervision to perform still a breadth of skills, but also be able to perform a breadth of more complex skills. And in particular, this is kind of the high-level approach that I mentioned before. What we wanted to do is we collected diverse demonstrations of many different types of tasks. And we wanted to use these demonstrations as a means to be able to figure out how to perform more complex tasks. And there's a number of different ways that we can use these demonstrations to improve things. So we can first use it to improve the model. We can take these demonstrations and add it to the data set and learn the model on that data set. And we can additionally use it to improve the other 2 things. And so what we do is we fit a model of the actions that the demonstrator would take given the current image. This is essentially through imitation learning, through supervised learning. And then we can use this model first to direct the data collection process, to explore in the ways that the human demonstrator would explore. And we can also use it to guide the planning process. And because we're using a sampling-based planning process, what we can do is we can additionally sample actions from this action proposal model in addition to random actions to guide the process towards the kinds of behaviors that the demonstrator might do. So in this work, we were focused on the case complex tasks that involve multiple different objects, essentially using objects as tools to accomplish goals. And so here are some examples of the demonstrations that we collected. These were collected with kinesthetic teaching, where a human is guiding the robot arm through the motions. And they were using tools in different ways, like pushing objects to different positions. And then here are some examples from the model, the action proposal model. So we see they can figure out that in this situation, some interesting things to do might be to use the tool and pick up the tool and move it in different ways, or pick up the white objects on the left. So how this works is we can specify the goal again, run guided visual planning guided by that action proposal model to figure out a sequence of actions that will use the tool to move the objects to the left. And then we can actually execute those actions on the robot to figure out, basically, to execute the actions and actually try to perform the task of moving the objects to the left. And so in the results, again, we can use a single model and a single approach for many different tasks. So we consider tasks that the robot had never seen before, like using a broom to push things into a dustpan, trying to reach objects that are out of the robot's reach. So in this case, the goal was to move the blue cylinder towards the robot, and we restricted the motion of the robot to be within that green rectangle, and it can figure out that it needs to use the hook in order to bring the object closer to itself. Also, unseen tool, so it had never seen sponges before, but can figure out it can figure out that if it grasps the sponge and moves it in a certain way, it can wipe the objects off the plate. We also gave it situations where there isn't really a conventional tool in the scene, but there's things like a water bottle, and it can figure out they can use the water bottle to accomplish the task. And then lastly, we looked at if it always uses the tool and if it can figure out when to use the tool and when not to use the tool. So in cases where there are two objects, it finds that it's most efficient to use the tool to push the objects. And in other situations where there's only a single object that it needs to move, it can figure out that the most efficient way to accomplish the task is just to use its arm to move the object to the goal. OK. Any questions on this before I move on to the next approach? OK. So I don't think I quite have time for inverse models, so I'm going to skip this and briefly talk about one last approach that you can do in some situations. So what this looks like is, in many situations, you don't necessarily need to predict the future images or predict everything about your state. You may be able to predict alternative quantities, maybe quantities that you care more about. For example, if you want to have a robot grasp things, you could predict, if I take the sequence of actions, will I successfully grasp the object? Or if you care about collision avoidance, you can predict, if I take this sequence of actions, will I collide? Or if I'm in a video game, what will my health and damage look like if I take this sequence of actions? And this can be quite nice, because then you're predicting these lower dimensional quantities based on the sequence of actions. There's also a very close connection to things like Q-learning, where your reward function corresponds to the probability of that event or that quantity. So this is if you're in settings where you can observe these task-relevant quantities, this approach makes a lot of sense. Though, of course, you still have to manually pick these quantities and must be able to directly observe them during training. OK. So to kind of review what I talked about with model-based reinforcement learning, you can generally view this approach as fitting a model and fitting a model with supervised learning, and then optimizing your policy with respect to that model by backpropagating or by sampling. There are a few different ways to correct for model errors, such as refitting the model with new data, replanting with MPC, or using local models. And if you want to do model-based RL from raw observations, you can learn a latent space. You can plan directly in your observation space. You can use inverse models, which I didn't quite talk about, and you can try to predict hand-specified quantities. I want to briefly talk about some of the kind of trade-offs between model-based approaches and model-free approaches. So in this talk, I focus on model-based approaches where it's very easy to collect data in a scalable way, because you don't need reward supervision during the data collection process. It's also possible to transfer across tasks and use this model for planning to accomplish a number of different tasks. It typically requires a smaller quantity of reward supervision, of human supervision, in order to learn tasks, because you're learning this dynamics model separately. So the downsides of model-based approaches is that they don't optimize for task performance. They're optimizing for a surrogate objective, which is your ability to model the world. And this can lead to challenges down the road. And sometimes it's also harder to learn a model of the world than to learn a policy. For example, if you want to pour water from one cup into another cup, modeling the fluid dynamics of the water is extremely challenging, while the motion itself is extremely simple. And then lastly, you often need some sort of assumptions in order to learn complex skills, like the spatula task that I mentioned before, such as assuming that you have some sort of continuity in your space, or that you can reset the environment after each trial in order to kind of learn that task. In contrast, model-free approaches make very little assumptions beyond a reward function, and they're very effective for learning complex policies. This is, of course, at the cost of requiring a lot of experience and requiring a lot of trial and error. And in practice, these methods are often not transferable across tasks. And it's worth mentioning that ultimately, I think that we want elements both of model-free learning and model-based learning. Yeah. Okay. So such that I get to, I have a bunch of suggested readings if you want to learn more about these sorts of things. My slides will be online afterwards, so if you want to dig into them, here they are. There's also further reading on using known models, on some of the approaches that I mentioned. I'll also briefly touch on, there's been a number of approaches on combining model-free and model-based approaches. This includes using rollouts from the models as experience, using the model as a baseline to reduce the variance of your policy gradient, using a model for exploration, trying to develop policies that can plan, and finally using a model-based look ahead with model-free approaches. So if you're interested in kind of some of these things, some of these references might be useful to you. Okay, and I want to conclude by talking about some of the open problems. And this is where I think there's, I don't know, this is, I think, the most exciting part, in my opinion. So the way that I like to think about some of the open problems is what's missing to enable robots to learn in the real world with minimal assumptions, and what is needed to move towards more intelligent decision-making in these environments. And so I think a couple of things that are missing, there's certainly many more things that are missing, but I'll touch on three things. The first is, how can agents learn new skills with small amounts of experience? I'll talk about what I mean by that in a minute. Second, how do we ensure that we can explore safely? In all the settings that I mentioned before, we are largely disregarding safety or putting in like hand constraints for dealing with safety. And then lastly, I talked about this a little bit as well, but defining rewards, defining goals, where they should come from. This is a really challenging problem, and I'll touch on this problem as well. So the next slides I want to talk about kind of initial approaches for solving these problems and what the big challenges are in these problems. And the first problem is, how can we learn new skills with small amounts of data? So I showed some approaches for generalizing to new tasks and learning skills from scratch from small amounts of data. But one of the things that strikes me is a huge difference between all the things that I presented today and kind of what humans are capable of doing is that humans aren't learning from scratch. So humans can't learn individual complex skills completely with a blank slate. They have a breadth of previous experience of exploration, and they use that in order to learn new tasks more quickly. And so maybe our agents shouldn't be learning from scratch. Maybe they should be building upon a breadth of experience. One of the approaches that I'm really excited about for trying to solve this problem is what's known as meta-learning or learning to learn. And what these approaches, the kind of key idea behind these approaches is to train a model across a breadth of prior data such that it can be quickly adapted to a new task, to a new object, to a new environment. For those of you familiar with Bayesian methods, this essentially corresponds to learning a prior such that that prior can be combined with small amounts of data to quickly learn new things. Right, so a couple of instantiations of what this can look like actually for robots in the real world. Some of the work that we did previously is training across many different objects such that when it sees a new object, it can very quickly adapt. So in this case, we were looking at imitation learning settings. If you try to run imitation learning from scratch, you need a lot of demonstrations to learn. And this work, we collected demonstrations across many different objects such that when it saw a demonstration for a new object, in this case, the goal is to place the peach into the red bowl, it can learn a policy for performing that task from just this one video demonstration. Even though it's never seen peaches before, it's never seen this red bowl before. And then it can also be adapting, instead of adapting to objects, it'd be adapting to environments. So we did some work in collaboration with Ron Fearing at Berkeley where we collected data across different terrains on this legged robot. And then we tried to have the robot adapt online to a new setting. So we trained it such that it could very quickly adapt to these terrains. We then actually took off its front right leg and tried to see if it could figure out how to adapt very quickly, in this case actually online with only a few times of experience, to this setting. And it's able to, in this case, adapt its dynamics model of the environment and figure out how to run in a straight line even though it's missing its front right leg. And then I guess if you're interested in learning more about meta learning, I'd be happy to talk more offline. This is actually what my entire thesis was on. And we also gave a tutorial at ICML a couple weeks ago on these types of approaches as well. Great. And then beyond approaches based on meta learning, there's also approaches that are trying to make existing algorithms more efficient, such as better off-policy learning, where you have a breadth of previous experience. You want to be able to use that previous experience even though it's collected from a different policy from the one you're currently considering. Better exploration methods, better self-supervised methods, considering options and hierarchical RL methods, and finally, leveraging stochastic policies for better exploration. If you could explore in a self-supervised way, in a way that allows you to perform new tasks more quickly, then you'll be able to kind of accomplish this goal on the top. Okay, the second thing that I mentioned was safety. This is something that is a bit less of a challenge in the manipulation domains that I mentioned before. But if you care about mobile robots that might bump into things, for example, there are approaches that try to incorporate uncertainty about your model to try to stay within the regions where you're more certain about what will happen. Approaches that learn from off-policy data, because if you can collect data from a human, for example, and learn from that data, then you don't have to actually be collecting data in the real world. Things like human interventions through the process, introducing probabilistic constraints about what parts of the state space you should stay within. And then finally, there's been a lot of work recently on trying to learn in simulation where things are nice and safe and clean, and trying to transfer that what's learned in simulation to the real world. Okay, and then the last thing I want to talk about is rewards and goals. This is a really challenging problem. Humans are amazing at this. Humans have some internal notion of reward somehow. If you know anything about that, let me know. I'm not from a cognitive science background or a neuroscience background. And the real world doesn't give you rewards, essentially. And so it's really important to think about what are ways we can get rewards and goals from humans to communicate those objectives. And that's essentially a prerequisite for being able to accomplish those goals. And approaches that try to solve this include inverse reinforcement learning. We're trying to invert the reinforcement learning process and figure out what is the reward for a given policy or for some behavior. Includes things like trying to learn from pairwise preferences of humans, as well as trying to cooperatively determine the reward function between the agent and the human. And then beyond rewards, you might think about, well, maybe there are other ways to represent the goal or represent the objective rather than the scalar reward function. And there are other ways that we can try to represent goals. This includes things like videos of humans, like I briefly mentioned before, providing an image of the goal, trying to specify where objects should move in the image, and language instructions. And things like language, I think, will be quite exciting to explore as it allows novices to communicate with robots as well. Okay. And I guess one thing I don't have too much time. We have some, I guess, very recent work that appeared at RSS like last week on this that I'm pretty excited about. I was going to quickly mention it. In this case, it actually gets back to one of the questions before. We're learning a classifier that kind of determines whether or not we've succeeded or not. And this classifier can serve as a reward function for reinforcement learning. And one of the kind of critical challenges here is where do you get negatives for training that classifier? And kind of one of the key insights of this work is that we can get negatives from the policy such that we don't exploit, such that the policy is actually being adversarially trained with this classifier to find kind of the states that actually are achieving the goal. And we additionally in this work looked at actually actively querying the user to figure out what states are good and what states are bad. And I guess the reason why I'm excited about this is that we applied it to things like draping towels onto objects. This is a task where, like, you can't specify a reward function without a significant amount of engineering. And so it really motivates the setting of trying to figure out how to learn a reward function, and the robot can figure out how to drape this towel, learn a reward function for effective draping, and also learn how to drape the towel. Okay, great. So for further resources on reinforcement learning, there's a number of courses. that I have linked here. I'd also be happy to talk more in person. I'd be happy to take more questions. Thank you.